So the defining property of this curve is that when you draw lines from any point on the curve to these two special thumbtack locations, the sum of the lengths of those lines is a constant, namely the length of the string. Each of these points is called a focus of your ellipse, collectively called foci. And fun fact, the word focus comes from the Latin for fireplace, since one of the first places where ellipses were studied was for orbits around the sun, a sort of fireplace of the solar system, sitting at one of the foci for a planet's orbit. Making up a little bit of terminology for ourselves, let's call this constant sum of the distances from any point on the ellipse to the two foci the focal sum of that ellipse. We'll get to the orbital mechanics in just a moment, but first, I want you to turn back to that construction that I showed at the very beginning, which is going to come up again later in the story. Remember, we take all of these lines from an eccentric point of the circle to its circumference and rotate each of them 90 degrees about its center. But what on earth does this have to do with the constant focal sum property I just described? You could just take my word for it that this emergent shape is an ellipse, but I think you'll be much more satisfied in the end if we take a little time right now for a brief sidestep into geometry proof land. First off, there are really only two special points in this diagram. There's the eccentric point from which all the lines emerge, and the center of the circle. So a reasonable guess would be that each of these is a focus of the ellipse. Given the defining property of an ellipse, you know that you're going to want to look at the sum of the distances from these 2 points to, well, something. Also, if you're doing any geometry problem involving a circle, you'll very likely want to draw a radius of that circle at some point, and to use the fact that this radius has a constant length, no matter where you draw it. I mean, that's what defines a circle, so you're probably going to need to incorporate that fact somewhere. With those two thoughts in the back of your mind, let's limit our attention to just one of these lines, touching some point P on the circle. Remember what happens in our construction. You rotate this line from the eccentric point 90 degrees about its center, and the geometry enthusiasts in the room might fancifully call this a perpendicular bisector of the original line. Now take a moment to think about the sum of the distances from our proposed focus points to any point Q along this perpendicular bisector. The key insight here is that you can find two congruent triangles and use them to conclude that the distance from Q to the eccentric point is the same as the distance from Q to P. So that means that adding the distances to each focus is the same as adding the distance from the center to Q, then Q to P. And there are two key things that I want you to notice here. First, at the point where this perpendicular bisector intersects the radius, that sum is clearly just the radius of the circle. And since that radius is constant, no matter where we draw it, the focal sum at that intersection point stays constant, which by definition means that it traces out an ellipse, specifically an ellipse whose focal sum is equal to the radius of the circle. Isn't that neat? And second, because the sum of these two lengths at every other point on that perpendicular bisector is larger than the radius, meaning the sum of the distances to the foci from those points is bigger than the ellipse's focal sum, all other points of this line have to lie outside the ellipse. What that means, and this is going to be important, is that this perpendicular bisector, the line that we got after our special 90-degree rotation, is tangent to the ellipse. So, the reason that all of the lines that we drew earlier make this ellipse appear from nothingness is because we're basically drawing a whole bunch of the tangent lines to that ellipse. The reason that that's going to be important, as you'll see later, is that this tangency direction is going to correspond to the velocity of an orbiting object. Okay, geometry proofing is done. On to some actual physics and orbital mechanics. The first fact is to use Kepler's very beautiful second law, which says that as an object orbits around the sun, the area it sweeps out during a given amount of time, like 1 day, is going to be constant, no matter where you are in the orbit. For example, maybe you think about a comet whose orbit is really skewed. Close to the sun, it's getting whipped around really quickly, so it covers a larger arc length during a given time interval. But farther away, it's moving slower, so it covers a shorter arc length during that same time. And this trade-off between the radius and the arc length balances out in just such a way that the swept out area is the same. A quick way to see why this is true is to leverage conservation of angular momentum. For any tiny little time step, delta t, the area swept out is basically a triangle, right? In principle, you should think of this as a very small sliver for a tiny time step, but I'm going to draw it nice and thick so that we can better see all of its parts. The area of this triangle is 1/2 base times height, right? That base is the distance to the sun. And what about the height, this little length here? How do you find that? Well, it's going to be the component of the object's velocity perpendicular to the line of the sun, what I'll call v perp, multiplied by the small duration of time. So the full area is 1/2 times the radius times v perp times delta t.